We spent a couple of videos naming amines. In this video, let's actually see how they might react. Now, to just kind of understand what happens with an amine, let's study one in particular. Let's look at ethylamine, and that's its common name. And that's obviously going to be a 2-carbon chain. So that's the ethyl part connected to a nitrogen. So that is the amine part. And then the nitrogen will have 2 other bonds, 2 hydrogens, just like that. And if you look at the periodic table, so here's our periodic table right here, you see nitrogen. You see nitrogen is in group 5. 1, 2, 3, 4, 5. This says group 15, but we're going to ignore the transition metals for now. So it has 5 valence electrons. When you look at it, when you look at the bonds here, you only see 1, 2, 3 valence electrons. So there's going to be 2 more, and they're going to be in a lone pair, just like that. Now, when you also look at the periodic table, you also see that nitrogen is pretty electronegative. It is pretty electronegative. In fact, there's only a few elements that are more electronegative. And remember, electronegativity is just how much does it like to hog electrons. So it's more electronegative than carbon. It's to the right of carbon. And it's way more electronegative than hydrogen. So if you compare it, not only does it have this lone pair of electrons right here, but it's also going to hog, let me do it in a different color. It's also going to hog these orange electrons, that are on the other side of the bond. So as we know, implicitly, there's a carbon right over here. There's another carbon over here. There's 2 hydrogens over here. We haven't drawn all of those stuff. But it's more electronegative than everything it's bonded to. So it's also going to attract those electrons. So it's going to have a partial negative charge. It's going to have a partial negative charge. And you're going to have a partial, let me make it very clear. The partial negative charge, that's a carbon right there. The partial negative charge is at the nitrogen itself. And you're going to have slightly partial positive charges at the carbons and the hydrogens, especially at the hydrogens. And now if we just talk about the properties of it, because it's polar, this would actually give it a reasonably high a melting and boiling point. You could imagine amines, when they are in a solution with other amines, are going to be attracted essentially via this type of hydrogen type bonding. The negative part of the partial negative nitrogens are going to be attracted to the partially positive hydrogens of other amines. Now, the hydrogen bonding for an amine is not going to be as strong as it will be for, say, waters or alcohols, because waters and alcohols involve oxygen. And oxygen is even more electronegative than nitrogen. So these partial charges are even stronger. So that's why hydrogen bonding is even stronger in the case of things that have oxygen in it, like alcohol or water. Now, with that said, let's think about how this might react. I have a lone pair over here. I also have a partial negative charge because this guy is more electronegative. It seems like we have a lot of negative action going around the nitrogen there. And because it has that, maybe it would either like to give away electrons or maybe take hydrogens from other things. And that, in fact, is the case with amines. So in general, and let me write this down. This is ethylamine right here, just so we get our naming practice. Ethylamine, this is the common name. We just said this is an ethyl group attached to an amine. And this is obviously a primary amine. It's only attached to 1 carbon right here. But in the case of an amine like this, and actually out of all of the functional groups we will look at, out of all of the neutral functional groups we look at, because of what we just described, because it has this partial negative charge, it has this lone pair, the nitrogen's pretty electronegative, this is actually the most basic, this isn't just ethylamine, this is all amines. Let me write this down. Amines are the most basic of the neutral functional groups. Obviously, something like a hydroxide anion, it has a negative charge. It will want to attract protons even more. But this one's pretty good considering that it is neutral. So given that it's basic, and we'll also say, and it's a related notion. It's also nucleophilic. And just as a reminder, when people talk about basicity, they're talking about how much does something want to give away electrons, or how much does it want to take protons. When you talk about nucleophilicity, or how good of a nucleophile something is, it's how good are you at giving away electrons, or how good are you at, well, essentially being attracted to protons, or giving away going and giving away electrons. And so when you talk about basicity, you're talking about a thermodynamic property. When you're talking about nucleophilicity, you're talking about a kinetic property. How good is it at interacting? The basics tells you how stable is it once it has interacted. So given that it's a nucleophile, you can imagine, I think you see where I might be going with this. Let me draw the ethylamine again. So ethylamine, I'll draw it in a little bit simpler. So let me draw the hydrogens like that. And then it has this lone pair. Let's think about what might happen if we have a solution of ethylamine. If we have ethylamine and it's mixed in with some bromoethane. So that's 2 carbons right there. Let me draw the bromo group. And it might not be obvious the way I drew this bromoethane right here. Let me write this down. This is bromoethane. But I think it will be obvious if I draw this carbon, right here, and if I draw the other 2 hydrogens, which are implicitly there. So that is 1 hydrogen right there, and then you have another hydrogen over here. And you have a good nucleophile in the ethylamine. So what do you think will happen? Well, you also have a good leaving group. So you see I'm talking in the language of Sn2 reactions. Or really, I'm talking in the language of nucleophilic substitution reactions. And I'm going to lean towards the Sn2 direction because I have a primary carbon here, good leaving group, pretty okay nucleophile. If this was a secondary, especially if this was a tertiary carbon, then I would be thinking Sn1. Then I would say, oh, maybe this leaves on its own. But in an Sn2, what we're going to have is this nucleophile will attack, or it'll give away its electron. So it'll give its electron to this carbon. And simultaneously, since this electron is going towards the partially positive carbon here, this bromine can finally take away that carbon's electrons. And so we just experienced an Sn2 reaction. This is an Sn2 reaction. And then after that is done, the bromine will have left. It has taken this electron. So it already had this one over here. It already had that one. And actually, it had another 6 electrons. 1, 2, 3, 4, 5, 6, 7 valence electrons for bromine. Now it'll have 8. So 1, 2, 3, 4, 5, 6, 7. Now it will have 8. It just took this one right here. It gained electrons, so it has a negative charge. And now let me draw this part right here. So we had this carbon. That hydrogen is sticking. Let me draw it like this. That hydrogen is sticking out, just like that. The other hydrogen is behind it. It's bonded to the other carbon up here. It's bonded to another carbon up here. That's really a CH3. It has 3 hydrogens off of it implicitly there. And now we've had the ethylamine has attached to it. So let me draw that. So then let me draw that. So that's the nitrogen, and it's bonded to 2 carbons, just like that. And then it has a hydrogen, and then you have this electron is still with the nitrogen, and then this magenta electron has been given to the carbon. It has been given to the carbon, just like that. And since the nitrogen has given away an electron, it now has a positive charge. It has a positive charge. So when you think about these 2 molecules, this molecule now has a positive charge. This molecule right now has a negative charge. So they would actually be ionically attracted to each other. And we've actually just formed a salt. And this would be called, and this is interesting here, or at least from a naming perspective, you have 2 ethyl groups. It might not be completely clear. You have 2 carbons here, and then you have another 2 carbons there. We could redraw this as, or we could rewrite it as NH2, and then we have 2 carbons, and then another 2 carbons, just like that. So we could call this diethyl. We have 1 ethyl, 2 ethyls. So this is diethyl. Let me color. So this, let me do a different color here. So you have an ethyl group right there and an ethyl group right there. So we call this is the common name for it, diethyl. And then you might want to call it diethylamine, but it's not ammonia, or it's not derivative of ammonia anymore. It's a derivative of ammonium, and that's because it's now positively charged. This nitrogen now has 4 bonds. So this is diethyl. This is diethyl ammonium. Ammonium. Diethyl ammonium is this molecule right here. And if you view it as a salt, and a salt is just a ionically, well, I don't want to go to the definition completely of a salt, but you view this as a salt because it's ionically bonded molecule. Where one of the molecules is diethyl ammonium, the other one will be bromide. This is the bromide anion right here. And you always list the cation first, the positive charged one first. So this is diethyl ammonium bromide, which we were able to form with the Sn2 reaction between ethylamine or ethylamine and bromoethane. Now, we can now go under another step here. If we have a ton of this ethylamine floating around, if we have an excess, and early on we will have a lot more of that than we will have of this thing right here. If we have a ton of ethylamine floating around, let me draw some ethylamine. If we have a ton of the ethylamine floating around, it might be able to grab one of the hydrogens from the diethyl ammonium over here. So you could imagine a situation where it grabs a hydrogen, essentially gives its electron to the hydrogen, and then that hydrogen's electron can be taken back by the nitrogen. And I'll draw this as an equilibrium because it's not really that much more likely that this guy takes away that guy's electron than that guy can take or could go and then take the electron back. So it's a reversible reaction. But if that were to happen, then this guy right over here will then look like this. You have the ethyl group bonded to a nitrogen that only has 1 hydrogen on it. Let me just draw it like this. A nitrogen that only has 1 hydrogen on it. And then he's bonded to another ethyl group. Right over there. And now he has his, so if you view this as an electron right there, he has his lone pair. So he took that it looks like yellow ochre, well, not, it's kind of a yellow-green color, took that back from the hydrogen and is now neutral, got an electron back. So now this is just diethyl ammonia. This is just diethyl ammonia. This is diethyl ammonia. Actually, no, sorry, it wouldn't be diethyl ammonia. It would be diethylamine. Sorry about that. Let me erase that. This would be diethylamine. Diethylamine. It would be ammonia. Ammonia is just NH. NH, let me draw it like this. Ammonia, just to make things clear, is this. And that's why my brain was telling us to go ammonia. And then ammonium is this. Ammonium is this. Give away one of these electrons to a hydrogen proton, you have a positive charge. Now, when you do the common naming, when it's kind of ammonium derivative, you do say diethyl ammonium. And then my brain said, OK, now that we got rid of the hydrogen, I went back to ammonia. So I said diethyl ammonia, but that's wrong. Obviously, this is now an amine, so we use the common naming for amines, and we get back to diethylamine. And then this guy over here will turn into ammonium. Or sorry, this guy over here will turn into ethyl ammonium. Sorry for all the confusion. So this guy over here is a nitrogen, 2 hydrogens, ethyl group, and then he grabbed another hydrogen. So he grabbed this hydrogen over here, grabbed that hydrogen over here. So now he has a positive charge since he gave away that electron over there. So now he is ethyl ammonium. Ethyl ammonium. But this is reversible right here. But what you can see, through this Sn2 reaction, we were able to essentially get rid of one of these hydrogens and substitute it with another ethyl group. We went from having a primary amine, right? This is bonded to 1 carbon, to having a secondary amine through this Sn2 reaction. It's bonded to 2 carbons.